We're going to talk about limiting reagents. First, it's important to understand what are limiting reagents, or sometimes called limiting reactants. A limiting reagent, or a limiting reactant, is the reactant that completely reacts first in a chemical reaction. An example that helps people understand this concept is what I call the toy story. Let's propose a hypothetical situation where we are manufacturing a toy that is made of 2 parts of A and 1 part of B, and we're making a toy out of these 3 parts. 2 parts of A and 1 part of B. Since we're talking about chemistry, I'm going to write that in terms of a balanced reaction. 2A plus B yields C. 2 parts of A plus 1 part of B gives us our toy. Our toy is called C in this case. And in this example, we have 15 parts of A, 5 parts of B, and 0 toys initially made. And we want to ask, how many toys or how many C's can I make with this setup? Well, let's find out. We start with 0 toys, and we make 1 toy. When we make 1 toy, we now have 2 less parts of A and 1 less part of B. We now have 13 parts of A, 4 parts of B, and 1 toy made. Let's make another toy. When we make 2 toys, we have 11 parts of A remaining, 3 parts of B remaining, and 2 toys made. Let's continue this to 3 toys, 4 toys, and 5 toys. When we get to 5 toys, we are now run out of parts of B. We have 5 parts of A remaining and 0 parts of B remaining as well. But we have 5 toys initially made. We can no longer continue making toys because we do not have the required part of B to make 1 single more toy. So in this case, we would call B the limiting reagent because it ran out first, or what we say, reacted completely. We have parts of A left over, but B was the limiting reagent because it stopped the reaction, it stopped the manufacturing of this toy because there were no more parts remaining to make any more toys. Let's look at an example you might find in your chemistry course. Calculate the theoretical yield of CH3CH2Cl in grams from the reaction of 11.3 grams of ethanol and 13.48 grams of PCl3. We're given a reaction to go along with this problem. 3CH3CH2OH, which is ethanol, plus PCl3 yields 3CH3CH2Cl plus H3PO4. So we have 11.3 grams of CH3CH2OH, or ethanol, and 13.48 grams of PCl3. So how do we even know this is a limiting reagent problem? We know this is a limiting reagent problem because we're given 2 distinct amounts of reactant. We're given 11.3 grams of ethanol and 13.48 grams of PCl3. If this was not a limiting reagent problem, then it would be indicated in the problem that one of the reactants was in excess. However, both reactants are given distinct limited amounts. So we automatically know from looking at the problem that this is a limiting reagent problem. So how are we going to calculate the theoretical yield of CH3CH2Cl in this reaction, which is a limiting reagent problem? Step 1. Convert the mass of reactants to moles of reactants. So we're going to convert 11.3 grams of ethanol to moles of ethanol and 13.48 grams of PCl3 to moles of PCl3. We convert 11.3 grams of ethanol by dividing the 11.3 grams by the molar mass of ethanol, 46.07 grams per mole, to get 0.245 moles of ethanol. We do this again for PCl3. Of course, PCl3 has a different molar mass. In this case, it's 137.32 grams per mole, and we divide 13.48 grams by the molar mass and get 0.098 moles of PCl3. So I'm going to put our amount of moles under our reactants because we're not going to be worried about the grams anymore. We're just going to be concerned with moles from now on. Step 2. Identify the limiting reagent. How are we going to do this? What we're going to do is ask each reactant a question. And the question goes like this. I'm going to pick PCl3. I could pick ethanol, but I'm going to pick PCl3. And I'm going to ask PCl3 if we wanted to completely react 0.098 moles of PCl3, which is all the moles that we have, according to this reaction, how many moles of ethanol would we need to completely react 0.098 moles of PCl3? Well, from before, we know that A is PCl3, because that's what we have, and B is CH3CH2OH. That's what we're looking for. Our X is 1 from PCl3, and our Y is 3 from ethanol. If you're not familiar with the setup, please go back and review the stoichiometry video. From this, we're going to multiply 0.098 moles by Y over X, or 3 over 1, to get our moles of ethanol needed. And here we would need 0.294 moles of ethanol. Next we ask, do we have it? The answer is no. We don't have 0.294 moles of ethanol. We have 0.245 moles of ethanol, which is less than 0.294. So we don't have the amount of moles needed in ethanol to completely react 0.098 moles of PCl3. So we got the answer no. Now we're going to move on to ethanol and ask ethanol the same question. If we wanted to completely react 0.245 moles of ethanol, according to this reaction, how many moles of PCl3 would we need? A is ethanol, B is PCl3. We have ethanol, we're looking for PCl3. X is 3 from the coefficient in the balanced reaction, Y is 1 from the coefficient in balanced reaction for PCl3. We're now going to multiply 0.245 moles of ethanol times Y over X, or 1 over 3, to get 0.018 moles of PCl needed. So we would need 0.081 moles of PCl3. Now again, if you're not familiar with these calculations, or if you're not familiar with my setup, please go back and watch or rewatch or review the stoichiometry video. So we would need 0.081 moles of PCl3 to completely react 0.245 moles of ethanol. Again, we're going to ask, do we have it? The answer this time is yes. We do have 0.81 moles of PCl3 because we have 0.098 moles of PCl3, which is more than 0.081 moles. The reactant which answers yes to this question is the limiting reagent of the reaction. No matter how many reactants you have, this is a foolproof method which will give you the identity of the limiting reagent. You just have to find which reactant answers yes to this question. So now we've identified ethanol as the limiting reagent. I'm going to put ethanol in blue to identify it as our limiting reagent. Step 3. How many moles of product, or in this case, how many moles of CH3CH2Cl are produced? Since we have moles of ethanol, and we're looking for moles of CH3CH2Cl, A is ethanol, and B is CH3CH2Cl. X is the coefficient in front of ethanol, which is 3, and Y is the coefficient in front of CH3CH2Cl, which is also 3. So we're going to multiply our 0.245 moles of ethanol by Y over X, or 3 over 3, to get 0.245 moles of CH3CH2Cl produced. Step 4. Convert moles to mass. In this case, we're going to convert it to grams. We're going to convert 0.245 moles of CH3CH2 to mass in grams. We do this by multiplying 0.245 moles of CH3CH2Cl by 64.52 grams per mole, which is its molar mass, to get 15.81 grams of CH3CH2Cl as our final answer. Next, we're asked, if the actual yield is 12.4 grams of CH3CH2Cl, what is the percent yield? So we're dealing with the same problem, but now we're asked if the actual yield is 12.4 grams of CH3CH2Cl, what is the percent yield? The percent yield is equal to the actual yield divided by the theoretical yield times 100. We can plug in moles or grams as the actual and theoretical yield, but it's best to work with the given. In this case, we're given grams, so we're going to plug in grams for the actual yield and the theoretical yield, because it would be much easier to just plug in grams since we have all that than to convert everything back to moles. Our theoretical yield is 15.81 grams, which we predicted from the previous part of the problem, and we just plug in everything from there. Percent yield is equal to 12.4 grams divided by 15.81 grams times 100, which is 78.43% yield. Find the grams of HBF4 formed when 0.409 moles of BF3 reacts with 0.313 moles of H2O. We're given a reaction. 4BF3 plus 3H2O yields 1H3BO3 plus 3HBF4. We have 0.409 moles, and we have 0.313 moles of H2O. Again, we can see this is a limiting reagent problem because we have two distinct amounts of reactant. We don't have any reactants which are in excess. We have distinct limited amounts of reactant, a limited amount of BF3 and a limited amount of H2O. Therefore, we know this is a limiting reagent problem, and we have to go through the steps of solving the limiting reagent problem. Step 1. Convert the mass of reactants to moles of reactants. Since we're given moles already, this step is unnecessary. The work was done for us. Step 2. Identify the limiting reagent. Again, we're going to ask each reactant a question and find out which reactant is the limiting reagent. So I'm going to pick BF3 and ask if we wanted to completely react 0.409 moles of BF3 according to this reaction, how many moles of H2O would we need? In this case, we have BF3, we're looking for H2O, A is BF3, B is H2O, X is 4, that's the coefficient in front of BF3, Y is 3, because that's the coefficient in front of H2O, and we multiply 0.409 moles times y over x, or 3 over 4, to get 0.307 moles of H2O needed. Do we have it? Yes, we do have it. We have 0.307 moles because we have 0.313 moles of H2O, which is slightly more than 0.307, but we do have it. The answer is yes, which means that BF3 is the limiting reagent. The reactant which answers yes is always the limiting reagent. But to make sure, let's do the same thing for H2O. If we wanted to completely react 0.313 moles of H2O, according to this reaction, how many moles of BF3 would we need? We're looking for BF3, we have H2O, X is the coefficient in front of H2O, which is 3, Y is the coefficient in front of BF3, which is 4. We multiply 0.313 moles of H2O times 4 over 3, which is Y over X, and get 0.417 moles of BF3 needed. Do we have it? No, we don't have it as we expected, because we've already identified BF3 to be our limiting reagent. We don't have 0.417 moles of BF3 because we only have 0.409 moles, which is again slightly less than 0.417, but we don't have it. So we know BF3 is the limiting reagent, and I've put it in blue so we know to remember that is the limiting reagent. Step 3. How many moles of product, in this case HBF4, are produced? We have BF3, we're looking for HBF4. A is BF3, B is HBF4, X is the coefficient in front of BF3, which is 4, Y is the coefficient in front of HBF4, which is 3. We multiply 0.409 moles of BF3 times Y over X, or 3 over 4, to get 0.307 moles of HBF4 produced. Step 4. Convert moles to mass, in this case grams. So we're going to convert 0.307 moles of HBF4 to grams. We do this by multiplying the moles of HBF4 by its molar mass of 87.881 grams per mole and get 26.96 grams of HBF4, which answers the question. Find the grams of NaNO2 produced when 154 grams of Na2CO3 reacts with 105 grams of NO and 75.0 grams of O2. And we're given a reaction: 2 Na2CO3 plus 4 NO plus O2 yields 4 NaNO2 plus 2 CO2. So in this case, we have 154 grams of Na2CO3, 105 grams of NO, and 75.0 grams of O2. And since we are dealing with 3 distinct limited amounts of reactant, we know that we're dealing with a limiting reagent problem. And as with all limiting reagent problems, our first step is to always convert the given mass of reactants to moles. So here we'll start with Na2CO3 by dividing 154 grams of Na2CO3 by its molar mass of 105.998 grams per mole to give 1.45 moles of Na2CO3. We'll do it again for NO. 105 grams of NO divided by its molar mass of 30.006 grams per mole gives us 3.50 moles of NO. And finally for O2, 75.0 grams of O2 divided by its molar mass of 31.998 grams per mole gives us 2.34 moles of O2. So that completes step 1 by converting our given mass of reactants to moles. And as with always, our step 2 is to now identify our limiting reagent. Now here, since we're given 3 distinct limited amounts of reactant, we have to ask each reactant 2 sets of questions. And each of those questions for each reactant must answer both to be yes for us to identify the limiting reagent. We can't have one yes and one no. Both questions have to answer yes in order for us to identify the limiting reagent. So we'll put our number of moles up here to clean it up, and we'll start by asking Na2CO3 if we wanted to completely react 1.45 moles of Na2CO3. According to this reaction, how many moles of NO would we need? We have Na2CO3, we're looking for NO, the coefficient in front of Na2CO3 is 2, the coefficient in front of NO is 4, so we simply multiply 1.45 moles of Na2CO3 by y over x, or 4 over 2, to give 2.90 moles of NO. So we would need 2.90 moles of NO to completely react 1.45 moles of Na2CO3. Do we have it? Yes, we do. We do have more than 2.90 moles of NO. We have 3.50 moles of NO. So we have more than enough to react all the Na2CO3. So let's move on to asking Na2CO3 if we wanted to completely react 1.45 moles of Na2CO3. According to this reaction, how many moles of O2 would we need? Now, in this case, we have Na2CO3. We're looking for O2. The coefficient in front of Na2CO3 is 2. The coefficient in front of O2 is 1, which means that we simply multiply 1.45 moles of Na2CO3 by 1 over 2 to give 0.725 moles of O2. So we would need 0.725 moles of O2 to completely react 1.45 moles of Na2CO3. Do we have that? Yes, we do again. We have more than 0.725 moles of O2 because we have 2.34 moles of O2. So in this case, we've already identified our limiting reagent because both questions for Na2CO3 have answered yes. But to be thorough, we're going to ask the remaining two reactants, NO and O2, the same two questions in order to see that we will only get yes for both answers for Na2CO3. So now we're going to move on with NO and ask the question, if we want to completely react 3.50 moles of NO according to this reaction, how many moles of Na2CO3 will we need? In this case, we have NO. We're looking for Na2CO3. The coefficient in front of NO is 4. The coefficient in front of Na2CO3 is 2. So to find out how many moles we would need, we multiply 3.50 by 2 over 4 to give 1.75 moles of Na2CO3. And now, do we have this? The answer is no, we do not have it. We need 1.75 moles of Na2CO3, but we only have 1.45 moles of Na2CO3, so we don't have it. Now to move on, 3.50 moles of NO, if we want to completely react that amount, how many moles of O2 would we need? So since now we have NO, we're looking for O2. The coefficient in front of NO is 4. The coefficient in front of O2 is 1. So we now multiply 3.50 moles of NO by 1 over 4 to give 0.875 moles of O2 needed. So we would need 0.875 moles of O2 to completely react the 3.50 moles of NO. Do we have that? Yes, we do have that amount. We need 0.875 moles of O2, but we do have 2.34 moles. We do have it, so the answer is yes. But since we already got the answer no, when we asked NO how many moles of Na2CO3 will we need to react 3.50 moles of NO, we already got no for that question. So in this case, NO cannot be the limiting reagent because we have to get the answer yes for both questions. And finally, we'll do this again for O2. If we wanted to completely react 2.34 moles of O2, according to this reaction, how many moles of Na2CO3 will we need? So now we have O2. We're looking for Na2CO3. The coefficient in front of O2 is 1. The coefficient in front of Na2CO3 is 2. So to find out how many moles of Na2CO3 we would need, we multiply 2.34 moles of O2 by 2 over 1 to give 4.68 moles of Na2CO3 needed. Do we have it? No, we don't have 4.68 moles of Na2CO3 because we only have 1.45 moles. And finally, the last question, if we wanted to completely react 2.34 moles of O2, according to this reaction, how many moles of NO would we need? So finally, we have O2. we're looking for NO. The coefficient in front of O2 is 1. The coefficient in front of NO is 4. So to find out how many moles of NO we need, we simply multiply 2.34 moles of O2 by 4 over 1 to give 9.36 moles of NO needed. And as we would expect, we don't have that amount because we only have 2.34 moles while we would need 9.36 moles. So as we've gone through these 6 questions, we've correctly identified Na2CO3 to be our limiting reagent. And because it's our limiting reagent, we're going to put our 1.45 moles of Na2CO3 in blue. So now we're going to go ahead and solve the stoichiometry problem since we've identified the limiting reagent. And in order to solve this problem, we need to find out how many moles of product, or NaNO2, are produced, because we want to find the amount of grams of NaNO2 produced when we have this mixture of reactants as stated in the original problem statement. And since we need our number of grams of NaNO2, we first need to find out how many moles of NaNO2. Now, since we know Na2CO3 is our limiting reagent, we have Na2CO3, and now we're looking for NaNO2. The coefficient in front of Na2CO3 is 2. The coefficient in front of NaNO2 is 4. So to find out how many moles of product, or NaNO2, are produced in this case, we multiply our 1.45 moles of NaNO2, or rather Na2CO3, by 4 over 2 to get 2.90 moles of NaNO2 produced. So that's how many moles of NaNO2 produced. Now we're going to convert our moles of product, our moles of NaNO2, to grams to answer the question. So we do that by simply multiplying 2.90 moles of NaNO2 by its molar mass of 68.995 grams per mole to give an answer of 200.1 grams of NaNO2. Next we're asked, which reactants are in excess and how many grams of each are left after the reaction? Now, since we've already identified Na2CO3 to be our limiting reagent, we know by definition that no Na2CO3 is going to remain, because limiting reagents are the reactants that are completely consumed or completely reacted first. So we know that no Na2CO3 remains after the reaction, which means that NO and O2 are in excess. So in order to find out how many grams of each are left after the reaction, we need to find out how much of NO and O2 are consumed in the reaction. So we can start with NO by asking the question, how many moles of NO are reacted with our limiting reagent, 1.45 moles of Na2CO3? So this is again simple stoichiometry, where we have Na2CO3, we're looking for NO, the coefficient in front of Na2CO3 is 2, the coefficient in front of NO is 4, so to find out how many moles of NO are reacted with the 1.45 moles of Na2CO3, we multiply 1.45 by 4 over 2 to give 2.90 moles of NO reacted. So now we've answered the question, how much of that NO is reacted? And in order to find out how much is left after the reaction, we simply subtract our 2.90 moles of reacted NO from our 3.50 moles of initial NO to give 0.60 moles of excess NO. And finally, we can multiply our 0.60 moles of NO by its molar mass of 30.006 grams per mole to give 18.00 grams of NO in excess. We do the same thing for O2. How many moles of O2 are reacted with 1.45 moles of Na2CO3? So again, we have Na2CO3, we're looking for O2. The coefficient in front of Na2CO3 is 2. The coefficient in front of O2 is 1. So to find out how many moles are reacted, we multiply 1.45 by 1 over 2 to give 0.725 moles of O2 reacted. And in order to find out how many moles in excess, we subtract our 0.725 moles reacted by our 2.34 initial moles of O2 to give 1.615 moles of O2 in excess.
And finally, to answer how many grams of O2 are left, we multiply 1.615 moles of O2 by its molar mass of 31.998 grams per mole to give 51.68 grams of O2 in excess.